Okay, the next thing we're going to talk about is Coulomb's law. So again, I'm going to read through these points here, and then I'll go through them in a bit more detail. So just reading number one, box number one here. Augustin de Coulomb, 1736-1806, studied the force of attraction or repulsion between 2-point charges, that is, charged bodies whose size are small compared with distance between them. Through various ingenious experiments, he was able to work out the following. So I'm going to read box 2 before I discuss it. The force of attraction or repulsion between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So what we're saying here is we've got if we put two charges here, so we can look at these two charges in space. There's a vacuum between them, nothing is joining them. This is just to show the lines of force and the distance between them. So here we've got charge Q1, charge Q2, and R is the distance between them. And force F2 is felt by Q1 from Q2, and a force F2 is felt by Q2 from Q1. Okay, and if we want to look at the actual force between these two charges, then it's simply the product of the two charges divided by the square of the distance between them. So if you want to really get a handle on that, it's very similar to Newton's inverse square law for gravitation. So you can think of these as two masses and the gravitational constant, and again it's the distance between them. So it's a very analogous formula. It's almost the same as Newton's formula in that respect. So again, if you just think of two charges at a certain value but a very long distance apart, a huge distance apart, and obviously this in the denominator becomes very, very large, means we get a smaller force. So that makes sense. So when these two charges are a huge distance apart, the force reduces, very quickly, inversely to the square of the distance between them. So the further you go apart, the more this r squared thing is going to reduce the force. Similarly, if the charges get very, very close, then r becomes very, very small, and if you can imagine, in the extreme where r is 0, then you're going to get huge force. Well, they'll never actually be touching, but as they get close, you're going to get a larger force. Yeah. So that's Coulomb's law. So I'm going to read number 3. I might just repeat what I've just said, but I'll read it anyway. When the charges Q1 and Q2 are of different signs, the force is repulsive. Well, I didn't mention that. But when they are alike, the force is attractive. So that's important. So if one of these charges is plus and the other one is minus, then obviously what's happening is these forces are going to be inwards. They're going to be pointing in because the two charges are attractive. Now, if two charges are of the same polarity, if they're both, for example, electrons, then obviously the force is repulsive, as in this diagram here. You've got a repulsive force. So that's really what that's saying there. This is similar to the gravitational force law, but electrical interactions depend on electric charge, and unlike gravity force, can be either attractive or repulsive. So that's the difference between Newton's inverse square law for gravity, is that in this case we've got mass. You don't have negative mass or positive mass, as far as we're aware, but in this case you do have negative charge and positive charge. So that's the difference between the two. And also another huge difference is the strength of the force. The force with electric charges is huge in comparison to the force between masses with Newton's law. So yeah, so that's what that said. So we'll read number 4. We can incorporate both the magnitude and direction of the interaction force between two charged particles into a single vector equation. To do this, we use a unit vector, r, lying along the line joining Q1 and Q2, and in the direction of Q1 to Q2, as shown in the diagram. So we got a unit vector here, and it's showing the direction from Q1 to Q2. Now I'm going to be going over, in the next video, I'm going to be going over some of the maths. I'm going to cover unit vectors, cross product, dot product, so that, you know, if this doesn't make sense now, watch that video after this one, and then come back to this one. If the term unit vector doesn't mean anything to you, you might want to watch that one before continuing watching this. But I'll assume you have watched that, and I'll continue. So the unit, to do this, we have a unit vector, r hat, lying along the line joining Q1 and Q2, and in the direction of Q1 to Q2, as shown in the diagram. So when we write Q1 and Q2 in this fashion, and when we write Q1 before Q2, and we have a unit vector here, that is what we're implying. We're saying that Q1 is pointing towards Q2, and that's where we're going to take the unit vector from. And okay, so I'll just carry on reading this. The force F2 on Q2 is then given by this equation here, and force F1 on Q1 is given by this equation here. So so when two charges exert forces simultaneously on a third charge, the total force experienced by that charge is found to be the vector sum of the forces that the two charges will exert individually. This is an important property called the principle of superposition, and it also holds for any number of charges. So what this is referring to, if we had a lot of charges, then we would take each charge individually, work out the forces contributing to all the other charges, then take the next charge and do the same thing. We can add them all together. So that's really useful. So we can actually figure out the charge here by simply working out all of these for each charge, and we can just add them together, which makes it really a lot easier.